Today I was going to go through a couple of example data sets to show some of these exploratory techniques in action. So let's go look at a couple of data sets and let's play with some of the techniques that we've been learning about. So let's do cluster analysis, let's do principal components, let's do testing and convert to an FDR. I'll also comment on Bootstrap as an approach. So I have downloaded two data sets from eCampus under Data, and now I'm going to download their scripts. First one. Yes, I will talk. Yes, so I will talk about singular value decomposition today too. I'm going to get these data and script for Arabidopsis. And for mouse liver. Mouse liver. Okay, let's start. Let's start with mouse liver. Okay, so I have opened mouseliver.r. These are microarray data, so they're omics data, M by N matrix of numbers. Here's the description from the abstract for the paper. These were liver endoplasmic reticulum associated polysomes from leptin deficient males after overnight fasting. So what does that mean? These are mice, and the mice were subjected to fasting, and then we have numbers that quantify activity level of a specific collection of genes that are thought to possibly be affected by fasting. Remember that your body has the ability to respond to stimuli. So we have forced a stimulus on these mice. They have fasted. Now let's see what's going on in terms of their gene activity levels. All right. So we have two types of mice in the data. There are obese mice and there are lean mice. And we're going to be interested in structure within and between these categories. Let's see. So samples 1 through 5 are obese, samples 6 through 10. The first two samples within each group were subjected to fasting the night prior. Let's open these data real quick and take a peek. Which ones are they? They come from gds4506.soft. So I'm going to open that file in my text editor. Lots of descriptive stuff up at the top. And down here, closer to where the actual numbers of interest are, is some detail on what the columns represent. So the first column of numbers, GSM 9670008, this is an obese mouse. Okay, obese mouse. So I'm not sure what I was saying with this comment right here. The first two samples Okay, so we have each mouse can be characterized in terms of two things. We have two like factor variables that describe systematic differences between these mice. We can characterize them as being either obese or lean. So I'm going to create a categorical variable, like a covariate, for that comparison, obese versus lean. And the mice differed depending on whether they were forced to fast or not fast. So some of them were forced to fast the night before, and some of them were allowed to eat as much as they want. You know, they had food available. So we have 5 obese mice and 5 lean mice. The first 5 columns are obese, last 5 are lean. The first 2 of the obese group were subjected to fasting, and the others were not. Similarly, the first 2, and this is not clear from the text that I'm highlighting. I think I read this from the actual paper. The first 2 in the lean group were subjected to fasting, and the last 3 were not. So let's come back here. Let's read in the data. I'm going to pull out the meta stuff at the beginning, because I only want the numbers in the m by n matrix. The last row is just some garbage text. It's not an actual gene, so I'm going to pull that out. Let's separate out the identifier information, like gene names and stuff like that, since those aren't numeric variables, and I want to treat the numbers like they are numbers. And then let's take what's left, which are the intensities, and we'll log transform them. Then create a couple of covariates or factors, obese versus lean, and fast versus ad lib, eat as you wish, ad lib. Tidy up the column names just so they're a little more informative. M is the number of features, N is the number of individuals. Okay. So we have 45,000 genes. Were there any missing values? Table is .NAY. There is an NA. Which is .NAY. So row 16,476 has an NA in it. 16476. Looks like that. So there's one missing value. I don't know a story for that missing value. I'm not going to worry about it right now. It might throw a warning later. If it does, we'll worry about it then. But there's only one missing value. It's not a big deal. Okay, let's start looking at the data. Simplest thing to do with a data set is to make a picture with it. Make pictures, compute summary statistics. Before you start computing p-values and regression models and false discovery rates and stuff, you should always look at your data. So here are side-by-side box plots for these data. We have 10 arrays. First 5 are obese, last 5 are lean. And these box plots look immaculate, as in too pretty. I seriously doubt that if you were to run 10 mice through some instrument like one of these and make a histogram or a box plot of the numbers, that they would line up this well. In practice, you would see something like we've seen with other data, like the yeast data. Remember the yeast data? We made side-by-side box plots, and some of those boxes were all over the place. Hopefully it's not extreme, and definitely, hopefully, it's not that some of the meta variables that are in there, like who did the arrays, explain big systematic differences in the boxes. But I would expect plus or minus just random variability from array to array. These data, I would guess, have already been processed somehow. That might be referred to as normalization, where you take raw data and maybe you make one of these pictures and the boxes aren't lining up well. But these are all mice. They all should be pretty similar in terms of, these numbers that come out of this assay. So we could try to normalize the data in one of many ways, but the common theme of normalization is to try to remove systematic technical variation. Probably some automated algorithm for normalization has been applied to these data. Okay, so we have multivariate data, we have omics data, and what other kinds of things can we do to explore what the story is with these data? One thing we can do is clustering. So I'm going to do hierarchical clustering. I'm going to use Euclidean distance when I do this dist function on the transpose of y. What we're going to get is, remember, the dist function will compute pairwise distances between all the rows in whatever matrix you give it. So depending on what you want to look for structure with respect to, that will dictate how you call dist. I'm going to look for structure, for clusters among the individuals. I have 10 individuals, and let's look at which of those individuals are most like each other. So to do that, I need a 10 by 10 distance matrix, a matrix of distances. All the pairwise distances are in this matrix. I can do the dist function to do that. If I want 10 by 10, as in if I want to look at structure among the individuals, I need to transpose this, because dist will give you a p by p distance matrix, where p is the number of rows in your data set. So when I transpose y, that puts the individuals in the rows. When I call dist without any other arguments, I'm computing Euclidean distance. And remember, there are different ways to define distance. In particular, I usually think in terms of, do I want Euclidean distance or do I want correlation-based distance? And then the linkage method we're going to use is complete linkage. Remember what that talks about? Whenever you have two clusters that have multiple items inside of them, linkage speaks to how do you define the distance between those two clusters. So basically, if you have two clusters, one of them has, say, 3 individuals in it, and one of them has, say, 4 individuals in it, you could compute all the pairwise distances between those two clusters. Here's the 3 versus the 4. Do all the pairwise distances. And, for example, complete linkage would say, take the biggest of those differences, and that is the distance between the two clusters. Single linkage would say, take the smallest. Average linkage would say, take the average. Okay, so let's do hierarchical clustering. And then let's make 2 pictures that we've seen. One is the picture, the dendrogram, like the tree-based picture, and the other is the picture of merge heights that helps us to decide how many real clusters are there. Okay, let's look at the right side first. The scree plot is what we've called it. And what we're looking for, if you think about this point over here to the very far right, this represents the final merge in which everybody was put together into one cluster. When we went to the next merge, right, the y-axis on this picture on the right is corresponding to the distances that are being computed. So, for example, the distance between this group and that group is whatever that is, 350 or something. That's the biggest difference. That's the biggest distance that we could find according to this algorithm. So these 3 and those, however, those 7 are as different as they're the most different out of every possible place to draw a horizontal line in this picture here. The fact that after you, if you do this final merge, notice how the vertical height separating the previous one is noticeably higher than it had been before that. We start out by considering every individual as its own cluster, and then we start joining things. So first we put these 2 together, and then we put those 3 together, and then we put those 2 together, and so on. We're working our way up. Whenever there's points that don't differ obviously in the vertical direction, those correspond to joinings that do not really define what you would call a real cluster, 2 new clusters. So like, look at these 3 right here. These 3 down here. The first step was to join these 2. But then the very next step was to put this one in with them. So in the distances, the merge distances here are consistent. They're not, there was not a big jump. It was not hard to put this one in with those 2. So as I'm going from the left, I don't really believe that I'm creating a new cluster at this point, or at that point, or maybe not even at that point or that point. Because these jumps are kind of homogeneous, they all are roughly of the same magnitude, until we get out to this last one, where to join these last 2 things took a big jump. There was a big difference, big distance between these and those. These right here. So that's, the way I think of this picture is the dendrogram represents all possible clusterings, ranging from everybody's their own thing to everybody's just one big thing. And then it's kind of your subjective job to figure out where along this vertical path am I going to draw the line and say, like, for example, we could draw a horizontal line right here and say whatever falls below that, that's the real stuff. So there's 1, 2 things that got left out whenever I did that. Is that where I want to draw the line? Or do I want to draw it like down here, in which case I would say there's this, and there's 1, 2, 3 things off by themselves there. As you're going up this path, should I, what do I make about this point right here? I could ask. Okay, so if I think that that is big enough to call that as a real distinction between real clusters, then everything that fell after that is going to be treated like its own cluster. So at this point, what happened at this point right here? This was the merge that was just above 300. That's going to be this merge right here. I think. No, I think it's this one right here. 300 and a bit, 300 and a bit. This is a pretty, noticeably a bigger vertical jump than some of these other ones. You can kind of see that in the picture by the fact that these vertical heights are relatively small compared to this vertical height. So there is kind of a visual jump in how far we had to go from here where everybody was separate to here where those 2 chunks are together. But if I say that's a real cluster, then it's like I drew a horizontal line at this point, which means that everything that has not been joined yet at this point is treated as its own cluster. So if I said, yes, this is a real distinction, then I would be saying there is a cluster there, that's a cluster, and all 3 of those are clusters. because any join points that fall above that point didn't happen. I don't consider them. Another way to think about that is if I pick the last one only, there's 2 clusters that result. If that's the only real distinction, then there's 1, 2 clusters. If I do this one, then there's 3 clusters. There's this, and there's that, and there's those 2. If I do this one, then there's 4, ... So if I do 1, 2, 3, 4, 5, if I do this one, there would be 6 clusters. There would be this by itself. There would be that. There would be this. There would be that. There would be that. And there would be all 3 of these. So all that to say, the fact that this does look kind of substantial, but the rest of them don't, beyond there, means I don't want to pick it. I don't want to pick this spot. What I'm really looking for is so let me clarify, a place where there is a noticeable vertical jump continually from that point on. That seems to be a real source of structure in the data. So long story short, I would look at this pair of pictures and say there's 2 clusters that I feel confident saying exist. I would feel maybe like I'm over-interpreting the picture if I tried to go down and say that's real and therefore everything else above it is real. I try to be conservative or not overreach when I'm interpreting something like cluster analysis, because I can show you simulated cases where it might look like there's structure, but you simulate it where there is no structure. So I think it's fair to be conservative. You know, you could argue, is there really just 1 or 2 clusters, or maybe you should go down some? If there's an argument, I'm going to tend towards the conservative side, which is to say there's only 2 clusters. I don't really believe the finer details so much. Yes?
Can you talk about the usage of the cluster?
Usage of what?
And now we have the clusters. What we are going to do with it?
Okay. So what do we do with this? You know, what?
For the technician experiment, for example, we had that technician here and different use.
Yeah. So yeah, let's talk about what would you do? What have we learned? What has this helped us with, if anything? First, let's look at these data, and then let's remind ourselves about the yeast data, or let's go the other way around. For the yeast data, we looked at cluster analysis and side-by-side box plots and PCA, and we saw consistently there's structure in the data. And it seems to be attributable to technician differences and or year differences and or strain differences. So we, by looking at the data this way, know that there is systematic differences between those categories. What do we do about it? I guess what I do about it in the yeast case is I put an asterisk next to this data set in my mind. Something's not quite right about these data. I wouldn't expect to see such big differences between technicians. That's worrisome. And the fact that that technician issue is completely confounded with some of the strain effect, because only one technician did all the fuel arrays. So I really don't have any confidence in saying anything inferential about what's different between, say, fuel yeast and other yeast. So it could be that what I actually do with a picture like this for those data is go talk to the PI and say, you know, I wouldn't put much stock in these data. Next time, when you do this, randomize who prepares which array, you know, what year each array was for the different strains and stuff. So use it as a teaching moment, essentially. You know, you have worthless data, or pretty much worthless data.
Could you also like take all and actually
So you can, yeah, principal components, think of it as a way to represent the structure. The problem in the yeast case is even if you can represent the structure, like we just talked about what is the structure. The structure is technician A is different from technician B, seems to be. I could try to adjust for that, but what would I want to do at the end of the day? I might want to say which genes are different comparing fuel strain to wine strain, say. Let's go do t-tests and get p-values and FDRs and get a subset of genes that seem to be different between those two conditions. You cannot adjust for technician effect in that comparison because it is completely confounded with the difference you want to quantify. So how would you go to a gene? Is this gene different comparing fuel strain to wine strain? You would estimate that with an average in the fuel strain samples minus the average for the wine strain samples. And that difference, there's no way to disentangle the two contributors to that difference, two possible contributors to that difference. It could be completely technician difference. No difference between fuel arrays or fuel yeast and wine yeast. Or it could be the other way. It could be completely, genotype differences, technician doesn't have anything to do with it. Problem is when you have all of the fuel arrays done by technician X and all of the wine arrays done by technician Y, there's nothing you can do. There's no way to disentangle and say that whether the difference is technician or fuel or strain. Yeah, even if you use technician as an effect in your model. So suppose, let's just forget about.
Oh, because you're saying you're looking at the difference. But if you look at all the data as a whole, right?
Well, let's think. Suppose you have. Suppose we have 5 observations, or 3. Let's say there's Y1, 1, Y1, 2, Y1, 3. So this is fuel for a gene. Pick a gene. Suppose we just have 3 arrays for the fuel strain, and we have 3 arrays for the wine strain. And I want to test, is the mean for fuel the same as the mean for wine? Is this gene differentially expressed comparing these 2 strains? We might fit a model that was, consider a model that was like yi equals beta 0 plus beta 1 strain I plus beta 2 technician I plus random error. That's like an ANOVA model. It's a linear regression model, which is a special case of ANOVA. What I'm interested in is this coefficient right there because that's the strain effect. And I'm adjusting for technician. So it's like technician, I'm trying to treat technician like a confounding variable or a covariate or a predictor variable. The intuition is that by including a variable in the model like this, when your main interest is in something else, adjusts for the technician effect. So it does, in theory, it does what you're talking about. Would allow me to do inference on beta 1, which is this difference. Allows me to do inference on that, adjusting for technician. What it means to adjust for in a regression way is to go look at the strain difference within common levels of that, and then basically average them. So go get the strain effect for technician A and get the strain effect for technician B, and then kind of average them, do a weighted average of them. That way you've done it within technician, So the technician effect has been kind of incorporated into it. So if I tried to fit this model to these data, R would give me an error because it's going to try to go get strain effect for technician A and strain effect for technician B. So for technician A, we only have fuel arrays. I can't estimate a strain effect for technician A. Same thing for technician B because I only have wine arrays. So it will give you an error. It has to do, it's a statistical issue that it's perfect confounding. It's not possible to estimate beta 1 in this model. Okay, main thing is, a short recommendation is to always use randomization as much as possible. Who's going to run the different samples? Randomize it. What time are they going to be run? What week are they going to be run? What batch are they going to be run in? Randomize all of that stuff as much as possible. Or you can end up with an unpleasant situation like this one where you spent thousands of dollars on a data set and then you can't say anything.
So I guess the question is okay, so if your data isn't like the factor, how do you implement these components into something applicable instead of just looking at the cluster?
Okay, so let's go back to this example, the mouse liver example, which is not as I can't think of the word, not as bad as the yeast example. Here's our mouse liver example. We're just getting started. We did this experiment. We have scientific reasons for thinking that obese versus lean, that's interesting to study, and whether they fasted or didn't fast might be explanatory. So let's see what the data hold. Step one is to look at them, and we see evidence of some structure in the data. I would expect there to be some structure in the data. We did an experiment. Some of them fasted, some of them didn't. Some of them were obese, some of them weren't. So I would be kind of surprised if there was nothing in the data. And sure enough, there is something in the data, and it appears to be these three being different from everybody else. So what are these three? We have one obese who was allowed to eat ad lib. We have one lean who was forced to fast, and we have one lean that was forced or that was allowed to eat ad lib. Okay, I don't have a real cute story to give to that based on what I know of these data. But I can take this picture and my understanding of it to the PI and say, okay, first off, I don't see overwhelming evidence that there are differences between obese and lean and between fasting and not fasting. Maybe going into this picture, I might have expected to see here's obese clustered together and here's lean clustered together. And maybe even within obese, here's fasting clustered together and ad lib clustered together. And then over with lean, same thing. That would maybe make most sense based on what we did to collect the data. We didn't see that. I don't see strong evidence that there's structure between or within obese lean or within fasting and ad lib. The only structure I see evidence of is this one. And so I would go to the PI probably and say, let's look at what we know about these three samples. Is there anything unusual? That's all right. Is there anything unusual that we should be concerned about with these data? Could be a similar issue. These were all run one week and everybody else was run the next week maybe, or something like that. So I would use cluster analysis as kind of getting familiar with the data. Does it look like what I kind of expected? In this case, no, it doesn't really. If it doesn't look like what I expected, does it suggest something else that is worth looking into further? And yes, it does. I would want to go talk about these three samples. Is there anything that we could say that is unusual about them? If so, then try to fix it. Worst case scenario might be to remove them if they aren't really comparable to the rest. And then it might happen that if you remove them, that the structure you expected pops up. Once you got rid of those noisy outlying points, possibly, here's obese versus lean, feasting versus ad lib. Possibly. I don't know. If there was nothing that we could say, we could find nothing in our records that distinguishes these from everybody else, then my default advice is you don't really have any business getting rid of them, you know, because as far as you know, they are representative of the population you want to make inference on. So just because they throw off the picture from looking like you want it to, don't feel like you have, you know, freedom to just throw stuff out, try different things. If you can't argue that they are different systematically from everybody else, then arguably they belong in the sample. From that point, what do you ask? Well, then I might start thinking about technical limitations of this technology. You know, if these aren't supposed to be systematically different from those, but they are, could it be, you know, issues with the technology? Could it be that there's maybe an unobserved covariate that's important? You know, gender. What if these were 3 females and these were all males? We didn't write that down. Maybe we should have written that down. So that's the kind of things that I would do. I would not take this type of picture and submit it to a journal to be published, you know, because this stuff is subjective. I mean, this might be included in the paper, but just on its own, a cluster analysis is just like a fuzzy picture of a data set. So it's part of the whole process of exploring and getting to know a data set. Let's also do principal components and singular value decomposition, so I will comment on that. So first, let's do PCA. Principal component analysis. Okay. The data look like this. What issues are you aware of? What kind of things do you want to think about before you haul off and do, say, principal components? One of the issues that we talked about, there's 2 ways to do principal components. It's always doing something consistent. That is, it's taking a matrix and it's decomposing it into eigenvalues and eigenvectors. We said there were 2 ways to do that. And the main distinction between them is what? You remind me. So we have data, m by n. Based on the data, we could turn that into a sample covariance matrix, which if I want to explore structure among the columns, will be n by n. We could equivalently or differently go get a correlation matrix, n by n. PCA, all it is eigenvalues and eigenvectors of one of those. When would you pick one over the other? Argue to me that you should use R, based on what we said a time or 2 ago. Does anybody remember? What's the difference between doing PCA on S versus PCA on R, and when might you want one or the other? So the issue is one with scale, one having to do with scale. If you have variables that you're going to look for structure among, and some of them maybe are proportions, they live between 0 and 1, and then here's a variable that's like annual income, so thousands of dollars, hundreds of thousands of dollars maybe, I don't know. Big difference in scale. If you did PCA with those variables, without doing any adjustment or standardization, it would correspond to getting eigenvalues, eigenvectors of capital S, and all it would tell you is that the income variable is driving everything because it has such a big variance by itself. That's not really it wasn't very insightful. So what you would do instead is standardize the variables, subtract their mean, divide by their standard deviation. Now every variable has the same mean and the same standard deviation, and the only structure we're going to see has to do with co-relationships. As one variable goes above its average, what happens to another one? Do they tend to go together and stuff like that? Okay, so we are going to do, in this case, it really shouldn't matter because these are all roughly the same scale. I am, I guess, a proponent of always standardizing, though. It's just I don't know of a reason really not to. So I'm going to go ahead and standardize, even though I probably could get away without doing it. So let's do PCA, PRComp. I'll just pass in capital Y, and please standardize. True scale equals true.
How do you turn off the bar when it splits up the graphs?
If you have done something like this, like we did to set up 2 pictures per panel, and I want to go back to the way it was, I'm going to say instead of 1 row, 2 columns of pictures, let's just go back to 1 row, 1 column. So now the next picture I make will just be a single panel. Let's look at the results. Summary PCA. Okay, there's a missing value, and that is going to cause us a problem. So let's get rid of that missing value. Easiest way, or one easy way to do this is just to impute it. Imputing is not the best answer to missing data, but it's quick and dirty. So y, where y is NA, let's just replace that with the average value. Okay, what does that do?
So just put where's the y? Just say NA dot omit, and if the y in it, you'll just leave it out.
Okay, we'll do that. Let's just get rid of the missing value. So we'll do na.omit y. That's going to kill the whole row that had that na in it. That's okay. We got 45,000 more of them. Let me just make sure I didn't lose anything. So let's read this back in real quick.
What would be better? Getting a whole row when you have 45,000 data points, or getting one single observation for that?
So the question was, what would be better in this case? What would be maybe the best strategy for dealing with the NA? With 45,000 and there's only one that's got anything missing, I might look at that one first just to make sure it's not extremely interesting somehow. And assuming it's not, I would either impute that one missing value by plugging in maybe the average of the other values for that gene, or just drop the whole row. If you've got 45,000 and it doesn't look exceptional based on just a quick look at the numbers, maybe just get rid of it. But imputation is fairly common as well. I would not recommend going crazy with imputation though, because it has some issues. So we are going to do this, and let's see what we get. Okay, so let's look at the last output, the summary. Yes or no, is there any structure in the data? Why do you say that? Yes, so there is a component that explains a lot. By the way, I wanted to show you guys this. What does it look like if there is no structure? Let's make some really boring data. So like X is just independent and identically distributed normal data. So let's do 1,000 features, 3 samples, mean 0, variance 1 every single time, and there is no correlation. So here's an omics data set. It's got 3 individuals in it. And let's do PCA. There's no structure. Everybody's independent of everybody else. There's no comparison groups. There's no treatment effects. There's nothing. So let's do PCA PRComp X. we'll go ahead and standardize. Doesn't make any difference in this case. PCA, summary PCA. This is what you would expect to see if there was no structure. What PCA is doing is trying to find linear combinations of the variables that maximally explains things. If there is no story to explain, then any linear combination, could be expected to be just as informative as any other one, which means there is no optimal way to boil the variables down. You could pick any arbitrary boiling down. Here's some numbers. I would not put any stock whatsoever in these numbers. The reason I wouldn't is because all three of them were basically a third of the information. We couldn't explain it, so we just randomly picked 3 explanations and gave each of them equal weight. So to the extent that when you do this to your data, you see something not uniform like this, like in our case, 90% and then it drops way down, or the first few are high and then it drops way down. Indications of structure, quote, structure. Okay, so there is structure in these data because I can explain 90% of the variance. Okay. How can I interpret this? Once I know that I care about principal component 1, I might go look at the coefficients that define principal component 1. And roughly speaking, all of these coefficients are of the same magnitude and the same sign. So this is a common first principal component. It's an index-like component, as in the variables are all correlated with each other. So they all jointly, you get more information by including them all. And the best you can do is just average them up, basically. If there was no correlation between the variables, you wouldn't expect to see an index kind of thing. An index type principal component is typical of there being correlation between the variables. So the first principal component just says, yes, these are all correlated variables. Other than that, there's not a story. There's no, like, obese. It's not a contrast between obese and lean, for example. It's not a contrast between fasting and ad lib either. So I would say for these data, there's not a whole lot of structure other than just the fact that the variables are correlated. If we went back to the clustering picture, we might reconsider our interpretation of the clustering picture. The clustering picture seemed to suggest those 3 individuals belong together and are different from everybody else. Principal components did not really highlight those 3 individuals. So I'm not all that worried about those 3 individuals, even though clustering, visually it looked like they stood out. If they stood out both in that picture and in principal components, I'd be more worried about them. And I'm sorry that we ran out of time. Let me at least show you what SVD is doing. SVD is just like principal components. They're doing essentially the same thing. Principal components works with one of these guys. You take a covariance matrix or a correlation matrix and you decompose it. SVD works with this guy, a rectangular matrix, M by N. And it turns out that you can decompose a rectangular matrix in an informative way as well. You could say Y is equal to a matrix product of something called U times something called D times something called V. This is M by N, this is M by N, this is N by N diagonal, and this is N by N. V transpose, I think is the way we write it. When you do SVD, so all SVD is a matrix operation where you take a rectangular array and you decompose it into a product of 3 things. And then it turns out that this D is diagonal, as in zeros everywhere except the diagonal. And on the diagonal are the eigenvalues of one of these guys. So the numbers inside D are the same numbers that you would actually get from PCA. And the columns of V contain eigenvectors of these guys. The columns of U contain eigenvectors of a different covariance matrix, the one for the features. Sorry. You could get by, you wouldn't miss much in terms of detective work if you did PCA but not SVD. SVD I like in some cases because it is nice that it can be applied to the rectangular matrix itself, and then inside of it there are eigenvectors for considering structure among the features and eigenvectors for considering structure among the individuals. And you might be interested in looking at both. But they are doing exactly the same thing. PCA is eigendecomposition of a covariance or correlation matrix. SVD is a decomposition, singular value decomposition of the rectangular matrix itself. So I will, I guess, suggest don't worry too much about SVD. It doesn't add a whole lot over principal components. If you understand principal components, you can apply it and get the same information out as you would with SVD. I've emphasized SVD more in previous semesters, but PCA is growing on me. Go ahead. Yep. Yeah. So suppose we did SVD, and we got in the columns of V are they're eigenpatterns. They're patterns that define structure among the individuals. So a picture you could make is like subject index. If I have n arrays, maybe there's 1, 2, 3, ... n arrays. And on the y-axis would be the coefficients for the linear combination that best explains the data. So remember what we're doing with either of these, with principal components, we're finding a linear combination of the original variables such that the variance of that thing is as big as possible. Most informative way to take the original variables and linearly combine them. And it turns out the answer to that task, the most informative way, the A that has the biggest variance of that, is the eigenvector of whichever of these we started with. So let's call these coefficients. These are the coefficients of A. And if you look at them, like let's suppose 4, 5, 6. Let's suppose we have these individuals were treatment and these individuals were control. If I took the coefficients from A and drew a picture, I might see something like this. In which case, I'm seeing there is structure because I could look at the eigenvalues to figure out proportion of variance explained. So here's something that explains a lot of variance in the data. It's important. It's a real pattern. And what is it? It is a pattern that will contrast, because these coefficients are negative, it's going to contrast those individuals with these individuals whose coefficients are positive. So I would look at this picture as there's structure in the data to the tune of explaining X% of the variance, and the explanation for the structure, what it appears to be reflecting, is a difference between these comparison groups. So I like to make pictures like this. You can make similar pictures with PCA, though, that look at the actual coefficients of these A things. So the output of PCA tells you about, is there structure, yes and no? Yes or no? What proportion of variance can you explain? If there is structure, the next thing you want to know is what is the story behind the structure? And that has to do with inspecting these coefficients. These are coefficients that say to create the first principal component, you should do minus 0.32 times that column plus minus 0.31 times that column, and so on. by looking at these numbers or making a picture of the numbers. That's all this is. This picture is just a picture of these numbers. I'm just trying to inspect the numbers and get a feeling for like what is the story. Is it in, go ahead.
When you see a file in PCA, they just plot those, the principal components for each.
Depends on who's making the picture. Sometimes you will see a picture like that. Sometimes you will see a picture like this. PC1, PC2. So we have data Y, M by N. Suppose that E is the matrix that contains the eigenvectors of, say, the correlation matrix. Then if I did Y times E, I would have the principal components. In new variables, and the first two of them explain the data as much as possible. So maybe the first one explains 50%, second one explains 20%. Together, if I just focus on the first two principal components, I take my big high-dimensional data and I boil it down to a two-dimensional picture that I can actually look at. So also an interesting picture is this one, where you draw a scatter plot. Each one of my individuals, or each one of my features, has a value for PC1 and a value for PC2. Make a scatter plot. And if in this picture you see evidence of grouping, that's informative. That's like doing kind of like cluster analysis. It's not exactly cluster analysis, but you're saying I can essentially represent my data in just two dimensions. When I do it, that's what it looks like. So apparently there is structure in the data that says there's two groupings. So you will sometimes see a picture like this one. You will sometimes see a picture like this one. They are not saying the exact same thing, but they are informative in different ways.
You can, so if you have three principal components, you go to a third dimension.
You can do that?
Two, right?
Yes. So sometimes, depending on the software, you will see three principal components. It might be that the first two explain 50%, but the first three explain 75%. So you want to include that third one. So you could have PC1, PC2, PC3. And then it would be a similar game. Can you find, pockets of individuals that have been kind of spread apart? If so, then you might go click on these individuals and find out who's that, who's that, who's that. How are they different? What characterizes them? Oh, that's all technician A, so it must be a technician effect. Or that's all treatment groups, that must be, there's differences between treatment and not treatment, and so on. So principal components, I would say, think of it as a very useful tool for taking high-dimensional data and just looking at it. It's hard to look at high-dimensional data. PCA takes some time and some effort to get your head around what you're looking at, but it is a bona fide way to take high-dimensional stuff and look at it in the smaller dimensions. Informative way. Teaches you something about the data. Okay, we're out of time. Other questions? Okay, so loading stuff, like whenever there's unfortunately a fair amount of lingo that might be multiple terms for the exact same thing that's used by different software. For example, R, when we did PR comp, called these numbers rotation. That's what the label was. That harkens back to the mathematical ideas behind PCA, which is to take multidimensional data and rotate it so that it's optimally oriented. But all these are the eigenvectors of, in this case, the sample correlation matrix. You might see something called loadings, and loadings are going to be eigenvectors. So all you're doing with PCA is eigenvalues, eigenvectors. To me, that's the easiest thing to remember, whether they want to call it rotation or loadings or whatever. Somewhere in the output needs to be eigenvalues and eigenvectors, and that's all I need to really understand the data in terms of PCA. All right, better let you go. See you Wednesday.